I believe we are live on Facebook, and of course, we're recording to the cloud. So Bob, you have the floor.
Okay, I'm sharing my screen. Can people see it?
We got
Yes.
it.
And you can all hear me okay?
Yes.
Whether that's a good thing or not, I guess you'll let me know in about an hour or so. But I'm glad to be able to get started. So I just want to start off by first thanking Mike Deneen again for setting up this Zoom meeting. And I thank all of you for Zooming in tonight. It's great to be back again speaking to GAC. And I hope all of you are managing to stay healthy and safe during the pandemic. So I'm dedicating this talk tonight to the originally scheduled speaker, Dr. Patricia Ann Stratt, who, as Mike mentioned, passed away in late October from lung cancer. So she was going to talk about her work on the Viking labeled release experiment, which might have detected life on Mars in 1976. But I got to interview her a couple times before she passed away. She was very, extremely interesting and gracious. So I'm grateful that I got to know her remotely, at least in the final months of her life. She was the one who taught me how to put this background photo behind me during a Zoom meeting I had with her. So I appreciate that. And I want to dedicate the talk tonight to her memory. So as some of you might know, I gave a talk earlier today to the Liverpool Astronomical Society in England. It was about the same basic talk I gave to GAC a couple months ago about life in the universe. But they asked lots of questions, so I was on for nearly 3 hours. So I hope my voice will hold out for this talk. So the talk I'm giving tonight is basically a slightly updated version of a talk that I gave to several Pennsylvania amateur astronomy clubs a little over a year ago. And it was based on my June 2019 cover story in Astronomy Magazine about cosmic expansion and the latest measurements of what's called the Hubble constant, which is a measurement of how fast the universe is expanding right now. Now, that article was really about like what's happening right now. But as I was preparing the talk a year ago, I thought it might be better to convert the talk into kind of a general historical overview of cosmology starting, over 100 years ago. So this is covering this very exciting science and how it's progressed over the last century. But I will get to this Hubble controversy near the end of my talk. I should note that because of the nature of this talk, this subject, tonight's talk is going to be a little bit more technical than the talk I gave about astrobiology. And that's just something I'm trying to make this as non-technical as I can, but at times it is a little bit of a technical subject. So, cosmology is a big subject. It's literally the study of the origin and evolution of the universe. And it's come a long, long way in the past century. If we could wind back the clock to the early 1900s, like right around the turn of the century, most astronomers assumed that our Milky Way galaxy was the entire universe. And they believed that the universe was static, that it was neither expanding nor contracting. So I would argue that the astronomers of 120 years ago knew less than nothing about the size, origin, and nature of the universe, because almost all of their ideas were simply wrong. I mean, it was simply they hadn't developed the technology yet. It wasn't that they were less intelligent, but we needed like a long period of observational and theoretical development to make progress. So here's just an example. This is the galaxy M101. So in the early 1900s, astronomers called these spiral nebulae. Like another famous example is M51, the Whirlpool. But astronomers didn't know the distances to these objects. So they didn't know if they were separate island universes far outside the confines of the Milky Way, or if they were just clouds relatively nearby inside our own galaxy. So the first really significant observational advance in cosmology came in the 1910s when an American astronomer named Vesto Slipher, we see here on the left, started looking at these spiral nebulae and taking their spectra, and he was realizing that the ones that are fainter and thus presumably farther away are moving away from Earth faster than nearby ones. So, this was actually, it wasn't really understood at the time how groundbreaking these observations were. He was basically discovering the fact that the universe is expanding, but that idea, and this is going to be a recurring theme, that idea was just too far ahead of its time. So even Slipher himself never really reached that conclusion. It was just an idea that was too far ahead of its time. So as Slipher was doing these observations, the Europeans were fighting World War I, and Albert Einstein was laying the theoretical foundation for modern cosmology with his general theory of relativity, which he announced in 1916. But the idea of an expanding universe was even too much for Einstein, even though the equations of general relativity predict that the universe has to either be expanding or contracting. He believed that because of gravity was going to try to make the universe contract in on itself. So he introduced this term, which he called the cosmological constant. That's kind of the energy, the residual energy in space, in empty space, and that this would prop up the universe from collapsing upon itself. Well, when Hubble proved that the universe was expanding 25 years later, 15 years later, Einstein called this idea, his cosmological constant, his greatest scientific blunder. But as I will explain later, it might have been one of his greatest and keenest insights. So, and as you'll see in the talk tonight, women have made very, very fundamental contributions to cosmology, and none more so than Henrietta Leavitt, who we see here, who worked at the Harvard College Observatory. So in the early 1900s, she was studying a specific type of variable star called Cepheid variables in the Large Magellanic Cloud, which is one of the Milky Way satellite galaxies. And she came up with this plot at the lower left, noticing that the brighter Cepheids, and therefore more luminous, were brighten and fade with a longer period than the dimmer Cepheids. And she noted that there's a pretty straight linear relationship. And this had major implications. It meant that once astronomers knew distances to Cepheid variables in our own galaxy, they could just compare the luminosities of the Cepheids in our galaxy with Cepheids in other galaxies. And we know that, the brightness of an object falls off with the inverse square of the distance. So you can then use this method to measure the distances to other galaxies. And then this is where the great American astronomer enters the picture. So in 1924 and 25, he found 12 Cepheid variable stars brighten and fade in the Andromeda galaxy M31 and 22 in the galaxy M33. And by comparing monitoring them brightening and fading, measuring their luminosity, and then comparing them with the luminosity of Cepheids in our Milky Way galaxy, he proved to the satisfaction of the professional astronomical community that these galaxies were way beyond the Milky Way. His measurements were actually off quite a bit, but they were fundamentally correct in that M31 and M33 are separate island universes way beyond the Milky Way. Here's some of you can see at the lower right, one of his variables, and you can see he wrote at the upper right, VAR for variable. And so he watched these stars brighten and fade. And this was a monumental breakthrough in astronomy because astronomers suddenly realized that the universe is vastly larger than many of them had assumed. But once again, Hubble could not have made this discovery without the earlier work on Cepheids done by Henrietta Leavitt. So I just want to mention, and since Mario is right here on our Zoom, is that he, a member of GAC, is that he's actually done this experiment with Cepheids in the Andromeda Galaxy with his own home observatory in Gloucester. You can see a little bit left of center, there's 2 tick marks, and the star in between is called V1, and Mario's monitored it, its brightness changes with his telescope, repeating what Hubble did. But this is really cool. It means that amateur astronomers today with decent telescopes and CCD cameras can basically do the same research that Hubble was doing 100 years ago. So a few years later, after this discovery by Hubble, a great Belgian physicist and also a Catholic Jesuit priest named Georges Lemaitre argued that the recession of galaxies observed by Slipher a decade earlier was due to an expanding universe. And, you know, he was using Einstein's equations for general relativity. He calculated the expansion rate of the universe, which is now known as the Hubble constant, or sometimes I'll say H naught for short. And he was the first to propose what we now call the Big Bang Theory. He argued that the universe arose from a very hot and dense and compressed state, which he called the primeval atom, what we now call the Big Bang. So his ideas, once again, were too far ahead of their time for the 1920s. So not many people really read his papers or took his ideas seriously. The good news is he lived into the mid-60s and lived to see that many of his great ideas were proven correct before he died. And I'm really glad about that. Now, a few years after that, Hubble made his second great discovery of his career, and that's why we name the Hubble Space Telescope after him. He was working with a colleague we see here at the lower right, Milton Humason, and using the 100-inch telescope on Mount Wilson in California, they basically repeated the discovery that Slipher had made 10 years earlier, that if you look at these spiral, what were then called spiral nebula, by now we knew they were galaxies, spiral galaxies. The fainter the galaxy, the farther away it was, the faster it's moving away from us. But you know, compared to Slipher, Hubble and Humason had much better data, and they could see galaxies and Cepheid variables out to much greater distances. So this was really conclusive evidence that we live in an expanding universe, and many scientists accepted that idea despite their original reluctance. A notable exception was Hubble himself. He lived into the 1950s, and amazingly, and I don't fully understand why, but he never really fully accepted the ramifications of his greatest discovery. So what Hubble and Humason discovered, but it's now called the Hubble-Lemaitre law, is that there's a proportional relationship between distance and cosmic expansion. That means a galaxy that is twice as far from Earth as another galaxy will be moving away from us twice as fast, and 3 times the distance, 3 times the velocity. Now, this law implies a uniform cosmic expansion rate. That idea is now known to be oversimplified and not quite correct, but based on what they could do at the time, this was a very insightful and important discovery. So I've mentioned earlier about how you can use Cepheids to measure the distances to faraway galaxies. measuring a velocity is actually more straightforward. You take a spectrum of the galaxy and you see spectral lines. These are from, like hydrogen and oxygen and carbon inside the stars and gas clouds in these galaxies. Well, if you look to farther and farther galaxies, you can see here in this chart, the farther away the galaxy is, the more that those spectral lines are shifted toward longer, that is, redder wavelengths. That's why we call it a redshift. So that's how you measure the velocity, by pretty simple measurement with the galaxy's redshift. So, but I want to point out something important, and that is we now know that the cosmological redshift of these distant galaxies is not the same as a Doppler shift. And we hear Doppler shifts every time we're on the road driving. Imagine like, a truck coming and passing you. At first, its pitch gets higher and higher. And then as it approaches you, then it passes you. And as it moves ahead of you, its pitch gets lower and lower. That's a Doppler shift. That comes from sound waves being compressed during approach and stretched out as it recedes. Well, with the expansion of the universe, the redshift is literally due to the fact that expanding space is literally, as you see it in this illustration at the upper left, is literally stretching out the wavelength of light. That's what causes the expansion or the redshifts that we see in distant galaxies. So the effect is basically like, imagine you have a balloon and you paint some galaxies on the surface of the balloon, and then you blow up the balloon. Every galaxy is going to see every other galaxy moving away. There's no center in the surface of a balloon. That's the way the universe is. There's no center around which everything is moving away from the center. Every galaxy is moving away from every other galaxy, carried away by the expansion of the universe. So it's the expansion of space that causes the redshift that I've been talking about. So I want to point out then that after these groundbreaking, theoretical by Einstein and Lemaitre, observational by Hubble and Humason, cosmology stagnated for nearly 20 years. And, I've read books about this. There really was essentially no significant progress, either observationally or theoretically, during like the 30s and into the early and mid 40s, partially because of World War II. And it was during this period that the eminent British astronomer Arthur Eddington, who was a Quaker, stated this quote, which in 2020 hindsight, I find really, really amusing, because it reveals the reluctance of astronomers of his era to accept the idea of an expanding universe. So I'm just going to read this real quickly. Eddington said, "The theory of the expanding universe is, in some respects, so preposterous that we naturally hesitate before committing ourselves to it. It contains elements apparently so incredible that I feel almost an indignation that anyone should believe in it except myself." I think that encapsulates the idea perfectly. So I'm going to move ahead now to 1948, when there was a monumental breakthrough in cosmology, although it was not recognized at the time. There were two American physicists, Ralph Alpher and Robert Herman, who published one of the greatest theoretical papers in the history of science. And what they did is they basically they took this idea of cosmic expansion seriously, and they said, well, what if you run the movie backward, back to the early universe? And what they did is they calculated what must have happened in the early fireball from the early universe as it's hot and dense and expanding. What would the conditions be as that fireball expanded and cooled over several 100,000 years? So their paper showed that about 300,000 years after the Big Bang, the fireball had cooled enough that to about a temperature of 5,000 degrees Fahrenheit, that negatively charged electrons, because up to that point, the universe was so hot that electrons could not combine with atomic nuclei to form atoms. But once the universe reached this critical temperature, that then suddenly electrons could combine with a hydrogen and helium nuclei and form atoms like we see here on the right. We now call, and they also calculated brilliantly that this process would release a torrent of radiation of light, and that the expansion of the universe would have redshifted this light into the microwave part of the spectrum. So we now call this radiation the cosmic microwave background, or CMB for short. And basically all of the ideas in this paper were fundamentally correct. And even better, they calculated that this hot gas, because it originated from a very hot, dense state, had to be in thermal equilibrium, meaning that the gas was the same temperature everywhere. And a gas in thermal equilibrium produces a characteristic spectrum. So they predicted this spectrum of how intense this cosmic microwave background should appear at various wavelengths, that, as you go to shorter and shorter wavelength, it would first get brighter and brighter, and then it would peak and then fall off as you get to shorter and shorter wavelengths. And I want to emphasize again, and you've heard this before, this paper was too far ahead of its time. It was basically ignored. Very few scientists read it or took it seriously. And inexplicably, this work of genius was essentially forgotten for nearly 20 years, which prevented cosmology from moving forward for 2 decades. And another sad thing is the technology existed at the time to detect this cosmic microwave background. Another sad, I think a sad part of this story is that Alpher and Herman never received the credit that they deserved in their lifetimes, although now their work is fully appreciated. If you read, books about cosmology, they now get their full due. But they're both dead now, and their work was not appreciated in their lifetime. So then in 1964, the American astronomers, Robert Wilson on the left and Arno Penzias on the right, discovered the cosmic microwave background that Alpher and Herman had predicted 15 years earlier. But they hadn't read their paper. They discovered it serendipitously using this horn-shaped antenna in Holmdel, New Jersey, which is about halfway between Philadelphia and New York. And this discovery literally changed everything. It was such a powerful confirmation of the Big Bang Theory that it immediately gained widespread acceptance among astronomers and physicists. And it remains, I think, as all of you know, the dominant theory of cosmology to the present day. And I would say it was thanks to this discovery that cosmology is now a mature empirical science. Now, Penzias and Wilson deservedly won the 1978 Nobel Prize in Physics for this discovery, which is, to be frank, probably one of the 10 greatest discoveries in the entire history of science. So they deserve the Nobel Prize, but I would argue that Alpher and Herman, who were still alive at that time, also should have won a Nobel Prize for predicting this microwave background. And I know this is a little bit old-fashioned, but if any of you have a television that you can tune with an antenna and you tune it between channels, about 1% of the static that you'll see on your TV is actually due to the photons in the cosmic microwave background. But having said this, it's very difficult to study from Earth because you're looking through the atmosphere where there's a lot of, terrestrial contamination. So I want to just, as of the 1960s, late 60s, this is where things stood with the Big Bang Theory. And most of these ideas are still correct. The idea was that the universe came into being from a single moment, what we call the Big Bang. But the theory does not explain how it came into being. This is still an area of profound mystery. The Big Bang is essentially a theory of like right after the creation event that created the universe. It basically says, and we know this from the microwave background, that the universe originated in a hot and dense condition or state. This is a really key thing. There's no singular place where the Big Bang happened. It literally happened everywhere. It's a moment in time, not a place in space. It says that in every direction you look, galaxies in a given direction are moving away from us at roughly the same rate. And because astronomers can measure how fast the universe is expanding, they can then infer how long it has been expanding, and that means the age of the universe. So suddenly we have a tool for measuring how old the universe actually is. So this is kind of where things stood with the Hubble constant, or the slope, in the late 1960s. They realized that astronomers knew that the Hubble constant could help them determine the age of the universe, but their measurements were still kind of crude by modern standards. Now, I just want to mention this, that the units of measurement for the Hubble constant is kilometers per second per megaparsec, where a megaparsec is 3.26 million light years. But I think for tonight's discussion, you don't really need to think too much about this unit of measurement. So I mentioned earlier about using Cepheid variables. So you might have been wondering, how do we get the distance to Cepheid variables? And that's actually fairly straightforward. It comes from a method called parallax, and you can demonstrate this very simply yourself. If you just hold a finger up and put it in front of your face, in front of your nose, and then blink your eyes back and forth, open your left eye, then your right eye, left, right, you'll notice that your finger shifts relative to objects in the background. Your finger appears to be moving back and forth, even if you're holding it still. Well, if you know the distance between the pupils of your two eyes, which you can measure with a ruler, you can then use high school trigonometry by looking at that angle of shift. You can then measure the distance to your finger. So astronomers can do this because Earth revolves around the sun. And we know now the distance between the Earth and the sun is 93 million miles. So when Earth is on one side of its orbit, you can observe a star. And then when Earth is on, 6 months later, you observe the same star, and you can measure the shift of that star relative to background stars. And we know the baseline is 186,000 miles. And so this trigonometric method allows you to measure the distances to Cepheid variable stars in the Milky Way. And then, as I explained earlier, once you know that distance and you can measure how these Cepheids brighten and fade in distant galaxies, you can then compare their luminosity to those in the Milky Way, and that gives you a measurement to other galaxies, the distance. Now, this gets really complicated because we can only resolve Cepheids out to galaxies within a few 100 million light years, which is still relatively nearby universe. So astronomers have developed a whole bunch of other methods called the extragalactic distance ladder that can take them out to much greater distances, out to billions of light years. And this is extremely difficult, painstaking work using methods that have been worked out over many decades. And there's so many methods, it gets so complicated that I'm not going to discuss them in any more detail, but if you want, you can ask me about it during Q&A. So, but essentially, you use these parallax, Cepheids, and then these other tools to measure distances to more and more distant galaxies where they're so far away that their motion is completely dominated by the expansion of the universe. So efforts to measure the Hubble constant ramped up in the 1960s and 70s when astronomers came to fully appreciate its fundamental importance to understand the age and evolution of the universe. And there were two major groups doing this work. There was one group on the left led by Alan Sandage, who was actually a protege of Edwin Hubble. He was based at the Carnegie Observatories in Pasadena, California. And then there was another group led by the French-American astronomer Gerard de Vaucouleurs, who was based at the University of Texas at Austin. Now, the problem was that Sandage kept measuring Hubble constants to different galaxies that were around 50 to 55 kilometers per second per cubic parsec or megaparsec. He's getting results in the low 50s. De Vaucouleurs' group kept getting results around 100. So their results were off by a factor of 2. Now, I know we have this view of science as this, ideally it's an objective search for the truth, but these Hubble wars really degenerated into intense personal animosity between the members of these teams. You can read about that in a great book from the 1980s written by Dennis Overby called Lonely Hearts of the Cosmos. I mean, it got really, really intense and personal. So you always have to remember that science is conducted by human beings who have emotions and ambitions. Okay, so as astronomers are trying to measure the Hubble constant, astronomers, other scientists were making big advances in other fields. Now, for example, this goes all the way back to the 1930s. There was a Caltech astronomer named Fritz Zwicky who first proposed the idea that there's a lot more matter, gravitating matter, than what we could see in our telescopes. People didn't really take him seriously at the time, although they should have, but it took Vera Rubin, who died very recently. She did these really incredible measurements of the rotation rates of spiral galaxies and proved to pretty much the entire scientific community, to their satisfaction, that what we see in a spiral galaxy is just the tip of the iceberg, that there's a lot more matter in the universe than we can see with our telescopes. So we now call this stuff dark matter. And right now we know that it outweighs what we would consider like familiar atomic matter by a ratio of about 5.5 to 1. Also, in the late 1970s, two Soviet physicists, Alexei Starobinsky and Andrei Linde, he actually now works at Stanford in the US. And on the right, Alan Guth, who at the time worked at Stanford, but is now right there in Massachusetts at MIT, they independently conceived the idea of cosmic inflation. And that resolves some of the lingering problems that existed at that time in the Big Bang theory, such as why the universe on very large scales appears more or less the same in all directions. So here's basically what they said with inflation, is that in the very early universe, we're talking like a tiny infinitesimal fraction of a second after the Big Bang, that the universe went through this incredibly rapid expansion that doubled. Like there's one model that predicts it doubled in size in about 85 times in a tiny, tiny fraction of a second. So this was then kind of added on to the standard Big Bang model that existed as of the 1970s. So it's basically has made the Big Bang Theory a more complete theory. It did not replace the Big Bang, it just made it a more complete theory. And I just want to show you here, how the inflation differs from the standard model. Is you start off from a smaller seed, and then suddenly you inflate the universe where it expands exponentially, but then it reverts back to a normal standard cosmic expansion rate. So, this idea, has made several very compelling predictions for observed features of our universe. And that's why it remains a very popular theory to this day. And here is just one of what I would call a put up or shut up prediction that inflation made during the 1980s that it has since passed with flying colors. So according to the inflation model, this very rapid, this exponential cosmic expansion in the very early universe produced sound waves, acoustic waves that propagated through this hot, dense gas in the early universe. And these sound waves would cause matter to bunch up in certain places and to become more rarefied in other places. So it would be a way of taking this more or less even distribution of matter and making it slightly uneven. And they actually also predicted that the sound waves would produce a signature of hot and cold spots in the microwave background where the average size of one of these spots would be about 1 degree across on the sky. So that was like a really pretty impressive prediction that has since, and I'll talk about this in a few minutes, has been spectacularly confirmed by observation. And that is why inflation added on to the Big Bang remains the dominant theory in cosmology today. Now, as inflation was gaining traction in the 1980s, two astronomers right near Gloucester at Harvard, Margaret Geller and John Huckra, were doing surveys of how galaxies are distributed in the universe on very large scales. And they showed that galaxies are not uniformly distributed. They come in clusters that are sort of linked together by these long filaments. And you can see this in this diagram on the right, and you can kind of see that dark stick man figure. And this was revolutionary, groundbreaking work that showing how matter is distributed in the universe on a large scale. And once again, this was predicted by inflation that these sound waves would have taken the gas that early on was in thermal equilibrium and would make it slightly irregular, and that just the force of gravity would act on regions that had slightly higher density and kind of pull that into cosmic structures, kind of similar to what we see in this diagram on the right. I actually think that Geller and Huckra should have won the Nobel Prize for this work. Geller is still alive. I think she's in her mid-70s. John Huckra passed away in 2010. I actually played against him in softball in some games between the Harvard Astronomy Department and the Sky and Telescope staff. So in 1989, then, Hubble launched a satellite called the Cosmic Background Explorer, or COBE for short. And by flying above the atmosphere, it could make better measurements of this microwave background without the contamination of terrestrial sources. So it made really great measurements. And very shortly after it started making its observations, it basically measured the intensity of the radiation as a function of wavelength. You remember this graph I showed you earlier from Alpher and Herman, and this was an exact match between theory and observation. I mean, an exact match. You will never see this in science, a better, more precise, more beautiful match between theory and observation. And this really proves, I think, beyond all doubt, that the universe did in fact originate in a hot, dense state in a gas that was in near perfect thermal equilibrium. So anybody who doubts the Big Bang Theory has to be able to account for this graph, because it is incredibly compelling evidence. And two of the scientists on the COBE team won the 2006 Nobel Prize in physics for this work. COBE also measured temperature, and this made big headlines in the early 1990s. It measured this intensity of the microwave background across the sky, and it detected the predicted small scale temperature variations varying only by about 1 part in 10,000 that were predicted by inflation. So this map here produced by COBE gives us a snapshot of how matter was distributed in the universe at an age of, we now think it was about 380,000 years ago when the CMB was released. The pink areas are the hot spots. That's where matter in the early universe was slightly denser than normal. The blue areas are the opposite. So then, something got messed up with this slide. So I'm now going to jump ahead to 2001. NASA launched a follow-up satellite called the Wilkinson Microwave Anisotropy Probe, or WMAP for short, and it could measure these temperature variations at better angular resolution. So the results that came out a few years later were stunning, because the statistical pattern of these temperature variations were literally an exact match for the prediction of inflation. The average one of these hot and dark spots is basically 1 degree across on the sky, and that's exactly what inflation with these sound waves predicted. So once again, in this one, the yellow and red spots are where the CMB is slightly more intense, and the blue spots were slightly less intense. So where the hot spots would later grow because of gravity to become giant clusters of galaxies, the blue areas would evolve to become giant voids. Now, as this was even before WMAP launched, 2 teams of astronomers made an incredible discovery. I was working at Astronomy Magazine at the time as a senior editor, and this discovery blew my mind. And these 2 teams, there was one team led by, on the left, Brian Schmidt and Adam Rees. And I just got an email today from Adam Rees, says that he has new results coming out next week. And on the right is astronomer Sal Perlmutter. And what they discovered is that the universe's expansion rate is actually accelerating. In other words, the expansion of the universe is now getting faster and faster and faster. And that was the exact opposite of what they expected. They were trying to measure the rate at which the universe's expansion is slowing down because gravity is pulling on everything and trying to counteract cosmic expansion. So what is causing this acceleration? We still don't really know. The leading idea, we call it dark energy. The leading idea is going back to Einstein's cosmological constant. There's laboratory experiments that have proven that empty space has this latent residual energy. There's actually no such thing as empty space because all of space has energy, and maybe this energy is pushing the universe apart. There's actually, for very technical reasons you can ask me about in Q&A, there's some reasons to doubt that explanation, but right now that remains the leading explanation for dark energy. And these 3 great astronomers very deservedly won the 2011 Nobel Prize in Physics for this revolutionary discovery. And they made this discovery by calibrating and observing what are called type 1a supernovae. These are exploding stars that come from white dwarfs that accumulate too much matter. They become unstable. They literally blow up in these stupendous explosions that can be seen at distances with our modern telescopes, billions of light years distance. So you can see these things at much greater distances than you can see Cepheid variable stars. So astronomers over decades were calibrating the luminosities of these type 1a supernovae so that they could use them to measure distances to galaxies way beyond the distance at which you can see Cepheid variables. So this is once again work that was done over decades. And at right around the time or shortly after this discovery was made, there were still astronomers trying to measure the Hubble constant. And one of the major projects of the Hubble Space Telescope, which was called the Key Project, was to measure the Hubble constant, to measure the current modern day expansion rate of the universe. And these two astronomers led a big international team. We have Wendy Friedman at the top and Barry Medor at the bottom. And in 2002, they published their value of the Hubble constant, which was 72 plus or minus 8%. Now, remember earlier we had the competing values of 50 and 100. So they're pretty much splitting right down the middle. And because they were using better equipment, especially Hubble, and they were incredibly careful in their work, this is the value that astronomers pretty much accepted. This value that the Hubble constant is about 72. And as we'll hear in a few minutes, this value is held up very, very well. There's another charming aspect of this story, and that is that Wendy Friedman and Barry Medor are husband and wife. And as far as I know, they're very happily married. And it just shows that married couples can do great research working together. So what this Key Project did is they used Cepheid variables in our Milky Way galaxy, and then they used that to calibrate galaxies where we could see Cepheids, but then which had a type 1a supernova explode. And then you calibrate the type 1a supernovae and you go to increasingly distant galaxies to measure the cosmic expansion rate. But I want to emphasize again, this is painstaking research that was done over many, that was built on research done over many decades. So this chart then shows how our measurements of the Hubble constant narrowed over time, and starting around the year 2000, or really even before then, you can see the values are starting to converge around this value of around 70 kilometers per second per megaparsec. So if you combine all of this data, the WMAP data on the microwave background, the Hubble Key Project, the best measurements of dark matter, the best estimates for dark energy, cosmologists in the early part of this century combined all of that data to develop what they now call the Lambda CDM model of cosmology. Lambda is the idea that dark energy is the cosmological constant. Lambda is the symbol for that, the cosmological constant, this idea dating back to Einstein that space has this residual energy. CDM stands for cold dark matter. That's the idea that dark matter consists of slow-moving dark matter, elementary particles that don't emit or absorb or radiate light. So therefore, it remains very difficult to detect experimentally. So if you make these assumptions that dark energy is the cosmological constant, and that the dark matter is made up of these slow-moving, relatively massive elementary particles, you can create this cosmological model called Lambda CDM. and plugging in all the numbers, you get about 74% of all the energy in the universe is dark energy. About 22% of the energy in the universe is dark matter, and only about 4% is of the type of matter that we're familiar with. And using the WMAP data, they calculated an age of the universe of 13.7 billion years. So how do we test lambda CDM? Well, the best way to do it is with a computer simulation. And here we see a group, this is an international group called the Millennium Run. If I recall, the computers were actually based in Germany. But what they do is you take this early state of the universe dating back to the map of the microwave background, when the universe just had these very slight irregularities in the density of matter, but then you just let the universe expand in your computer using the equations of general relativity, and you plug in your best guesses for dark matter and dark energy, and you see what you get. So if you look at this simulation, when you get to the modern day universe, you can see at the panel on the right, this is what you get. You get similar to what Geller and Huckra were seeing back in the 1980s, this filamentary structure of galaxies distributed, along these filaments and congregating at these bright nodes in giant superclusters of galaxies. There's been now a more recent simulation. We did a cover story about this in Sky and Telescope called the Bolshoi simulation. Remember, this is really a 3D. We're really looking at this through 3 dimensions, but I can't really depict that on the computer screen. So then you might be asking, how do these maps, these predicted maps of large scale structure in the universe match reality? So here's our reality check. Comes from the Sloan Digital Sky Survey, which started in the 1990s and is still ongoing. Well, using this cutting edge CCD technology and other technologies where they can, on one night, measure the distance to dozens and dozens and dozens of galaxies and get their spectra and velocities, they've created these maps that go to much greater distance than Geller and Huckra. And I just want to go back and forth for a minute. They might not look alike because of the way they're being projected, but statistically, these maps are identical. In other words, lambda CDM, which predicts this certain structure on the universe based on assumptions on dark matter and dark energy and what they are, if you compare that prediction with the real universe, there is a very, very close match between theory and observation. And that gives cosmologists great confidence that their basic model of the universe is correct, at least in a general sense. And I firmly believe that this confidence is fully justified. So then in 2013, the Europeans had launched another microwave background satellite called Planck, and it came up with an even more detailed map than COBE and WMAP, even a higher angular resolution. Here we see their microwave background maps compared in resolution. So right now, the cosmologists are using the Planck data because that's the best data on how matter was distributed in the early universe. So now you plug these new numbers, slightly different than the WMAP numbers, and you plug that into lambda CDM, and you get these new numbers on the right where dark matter is 26.8%, ordinary matter is 4.9%, dark energy is 68.3%, and they just slightly change the age of the universe to 13.8 billion years. Now, the thing with Planck is you can then use that data to make a prediction of how fast the universe is expanding right now. That's the Hubble constant. And using this method, you get a Hubble constant of 67.4 plus or minus 0.5. So this is creating a tension in cosmology because the groups that are using these more traditional methods with the cosmic distance ladder that I've kind of already discussed are getting slightly higher values. They're still getting values in the low 70s. They're getting Hubble constants of about 73, and their measurements are using better and better instruments and better tools. So their measurements are getting more precise, but they're not agreeing with Planck. So this is just an example. These groups now have found and monitored eclipsing binary stars in the Large Magellanic Cloud that allows you to get even better calibrations, distances to the Cepheid variables in the Large Magellanic Cloud that Henrietta Leavitt was observing 100 years ago. They use a new European satellite called Gaia that gives much more precise parallax measurements to Cepheid variables. This is in space. You're not contaminated by the atmosphere. So you're getting better measurements to the Cepheid variables in our own galaxy, upon which all of this distance ladder is based upon. So the end result is that these measurements of the Hubble constant are getting more accurate and more precise. So one of the teams led by Adam Riess, one of the discoverers of the accelerating universe, came out with a result a couple years ago. His team is known as SHOES, and it measured a Hubble constant. This is actually its most recent measurement, a Hubble constant of 73.5, but only plus or minus 1.9%. So this agrees very well with the Key project that I talked about earlier, but this is a much more precise measurement. Their error bar was 8%. Riess's group is claiming an error range of less than 2%. Well, it gets better. There's another group. This is actually an offshoot of the Wendy Friedman group at Carnegie, led by this young astronomer, Chris Burns, doing basically the same kind of analysis, but looking at different galaxies than the SHOES team. He gets a Hubble constant, depending on which filter they use, once again, about 73 kilometers per second per megaparsec. This agrees very, very well with Adam Riess's group. And recently there's a third group that uses a different method of looking at gravitationally lensed quasars that gives you a more direct geometrical measurement of the Hubble constant. This group is co-led by Sherry Suyu. They come up with a Hubble constant of 73.3 plus or minus 2%. So, I mean, here we have it, that we have all of these groups that are doing these direct measurements in the local universe are all coming up with the same answer. Believe me, they're not arguing with each other, because they're within the range of error. They're all coming up with the same result, that the Hubble constant is about 73. But the CMB measurement, with our very best microwave background data and with this very well tested lambda CDM model, is predicting a Hubble constant of about a little more than 67. And these measurements now are so good and precise that you can see here that their error bars, their range of possible error, are not overlapping. So I've asked Adam Riess, I said, could this be, statistical chance or measurement error? And he said, quote, this is a direct quote, he said, there's a less than 0.01% chance of this kind of difference occurring just by chance. So this means that one of the two methods is wrong, or I think that this cosmic conundrum is more likely the result that we're missing something in our understanding of dark matter or dark energy. So, lambda CDM is spectacularly consistent with every astronomical and cosmological observation, but it contains a lot of unknown physics. We don't know what dark matter and we don't know what dark energy are. Combined, they make up 95% of the total mass energy in the universe. So one could argue, and I put this in my article, that it is an absolute miracle that this lambda CDM model works as well as it does when we really don't understand the underlying physics behind it. So, I'm confident that both of these teams, the Planck team, and then these various teams, the Shoes and Carnegie and Holy Cow teams, have done their measurements correctly. And so I think it's going to turn out that the resolution to this is going to be, there's still something missing in our overall understanding of the universe. And I want to also emphasize that this is not like the Hubble wars of the 60s and 70s. There's no personal animosity here. All the different groups respect the work that the other groups are doing. And now they realize there's a puzzle that we have to solve. So how are we going to solve this puzzle? There's a number of observations being done right now that could relieve some of this tension in the Hubble constant, and prove that I think that it's real. One method is to use these distant type 1a supernovae, and there's also other methods to get a more precise measurement of how the expansion of the universe, the rate of expansion, has changed over time. We already know that early in the universe, in the first 7 or 8 billion years, and you can see in this diagram, the cosmic expansion was slowing down because of gravity. But then about 5 billion years ago, it started to accelerate under the effects of dark energy. So we don't know exactly, we don't have really precise measurements yet of how the expansion rate has changed over time. But there are several groups doing this work, and we're going to get better information on this in the years ahead. There's also groups doing this with ground-based telescopes. They're not measuring the whole sky, but they're getting very high angular resolution of very small areas of sky, either with ground-based telescopes like at high altitude in Chile, in the Andes Mountains, or in Antarctica, or even on balloons. And they're also attempting to measure how these microwave photons in the CMB are polarized. And that will probably give us more information on, the Hubble constant and better parameters to plug into lambda CDM. And then that we've got LIGO and Virgo, which are detecting gravitational waves, including several now from merging neutron stars. And by detecting, once we get up to dozens of neutron star mergers, which should produce essentially identical gravitational wave signatures, we're going to get a better measurement of the Hubble constant from that down to about 1% accuracy. So I want to just conclude by saying that, despite all these tremendous advances that we have made in recent years in cosmology, I think we're still missing something fundamental in our understanding of the origin and evolution of the universe. If I had to bet money, I would bet that it has something to do with dark energy, which is, of course, the dominant form of energy in the universe. And dark energy is really important because it controls the universe's long-term fate. So depending on what form dark energy takes, the universe might expand forever, kind of at, a slowly accelerating rate. That's known as the Big Chill, where eventually all the stars die, black holes evaporate, and we're left with a sea of elementary particles at a fraction of a degree above absolute zero. There's another less pleasant fate known as the Big Rip, in which the accelerated expansion gets so powerful that it literally rips first atoms and atomic nuclei, and just rips everything apart. An incredibly violent fate for the universe. But then if dark energy is something other than the cosmological constant, if it's some kind of dynamical energy field that changes with time, that could maybe someday cause the universe to reverse its expansion and recollapse upon itself in a big crunch. And maybe then we get another big bang and the rebirth of the universe. So I'm really hoping that this Hubble tension gets resolved in my lifetime, and it tells us something really important about the ultimate fate of the universe. So I want to thank you all for being patient, and I will be very happy to take your questions, but I would really appreciate if you can give me a couple minutes just to run upstairs and grab a beer. So thank you.
All right, thank you, Bob. Grab a beer. We'll wait for you.
I'll be right there.
Ask him what, have him show you the label. It'll prove my point.
The label of the beer?
Yeah,
And what's your point?
he picks these bitter beers. I don't like them.
Oh,
I'm more of a Guinness guy.
so Mario, we're not going to be doing online stuff forever. You going to be in town anytime you can predict in the coming months?
I'm not going anywhere. Who
What
is?
about virtually?
What's that?
What about virtually? Of course, that's hard to predict when you're going to be called upon to be in a Zoom.
I have to look at my schedule. Are you talking about the that UN report?
Well, anything. Let's talk about you doing a
Cheers,
GAC
everyone.
session in the spring.
Okay, what's the, see, he won't even show you the label.
I'll show you the label.
Embarrassed by it.
You showed us the color. It didn't look too bad.
What is it?
It is a Trogs Lucky Holler Hazy IPA. And I drank one of these after I talked to the English group because IPA is a British style beer.
Yeah, it should be a good stout.
Oh, I have some stouts too.
All right,
So,
Bob,
but
why don't you unshare your screen unless you're going to use it to answer questions with?
Okay. Well, if I need to, I guess we can always go back to screen share, right?
Oh, yeah. Oh, yeah.
Okay, there we go. We're back now.
All right. This way we can see each other.
Yep.
Any questions for Bob?
Mike, just contact me and we'll work that out.
Okay, Mario, thanks.
I'm getting my first vaccine next Thursday or Friday.
Great. And you deserve it. Healthcare workers should be the first to get it.
So I have a question referring to your praise of Alpha and Herman. And so I was just wondering where the paper by Alpha, Beta, and Gamma fit in.
Okay, that's actually a very good question. There was a different paper where they were predicting, that was something I left out of the talk because for time consideration. I actually, when I first created this talk over a year ago, I had a slide for that. And then I realized the talk was, was going to be too long. So I cut that slide out. What they did, Alpha and Herman, and this was very important, Bill, so I'm really glad you asked this, is that they realized that in this fireball of the Big Bang, like right after the explosion, when the universe is set in motion, that the temperature and density conditions in this fireball would allow basically two types of atomic nuclei to form, hydrogen and helium. So that's what they predicted. And this paper came out like around the same time as their microwave background paper, although Gamow was not an author on that paper. So they predicted that the universe originated with about 75% hydrogen and 25% helium. And, that's been confirmed as well. If you look at kind of the very rarefied gas between galaxy clusters that hasn't been processed through stars. That's about 75% hydrogen and 25% helium. So that's another, and that's why I'm really glad you asked that question. That is another amazingly successful prediction of this Big Bang model. And, you know, another reason why Herman and Alpher should have won the Nobel Prize for their work.
And wasn't this lineup of authors a bit of a joke as well? Like
Yeah.
alpha, beta, gamma?
Yeah, that's right. That's right. Yeah, that's right. Alpha, beta, gamma. Yeah. And there's actually a famous picture that I originally included where they called this primordial soup, they called it YLEM, Yelem, which I guess is a Russian word because Gamow originally came from Russia and then emigrated to the US. But there's this funny picture of them where like Gamow is like a genie emanating from this bottle of Yelem with Alpher and Herman off to the side. It's a really, really funny picture. So they had a sense of humor. But, you know, I want to emphasize, I mean, that work they were doing in the late 40s, I mean, talk about brilliant. And, you know, so many of their ideas were confirmed. But a lot, you know, I think it's a real shame because the microwave background could have been discovered in the 40s. In fact, there was a British astronomer, I think his last name was McKellar, who actually did observations in the early days of World War II, where he basically found the microwave background, but didn't have a theoretical basis for interpreting what he found. So I sometimes wonder if, you know, the microwave background had been found in the late 40s or early 50s, that might have sped cosmology up by like 10 or 20 years. So it's kind of too bad that their paper was not really taken seriously at the time it came out. And we see that from time to time in science where, like another example is Alfred Wegener in the early 1900s came up with a theory of continental drift, but he didn't have a mechanism to explain how it worked. So his ideas weren't taken seriously. Well, now we know that we have plate tectonics, that his idea was fundamentally correct, but he was just too far ahead of his time. He was just, there are times in science where scientists come up with ideas that turn out to be correct, but it's just people don't have the mindset or the framework at that time to appreciate the genius of these ideas.
Bob, what's the process by which pigeon poop in a horn antenna becomes a cosmic microwave background?
I'm so glad you asked that question. So, you know, once again, I couldn't cover every story in depth. So this goes back to Penzias and Wilson with their discovery of the microwave background in the mid-1960s. Their original task, what was happening is this is right after the first communication satellites had been launched. And what was happening is that they were detecting this interference at specific wavelengths that was interfering with the satellite communication. So Bell Labs asked Penzias and Wilson to investigate this. So they're trying to eliminate all possible sources of microwaves. Well, one day they noticed that inside that horn antenna, there was some pigeon poop. And so they're wondering, could that somehow be related to this background noise that we're detecting? So they had to clean out the pigeon poop, but the signal did not go away. So the pigeon poop was not causing the microwave background. And the story gets really interesting because they're trying to figure out, well, what's going on? You know, they everywhere they point their antenna, they see this radiation in the microwave part of the spectrum. And they weren't aware of any of this theoretical work. So right down the road in Princeton, New Jersey, about 30, 40 miles away, they called up the Princeton group that was actually had done their own theoretical calculations. One of the members of this team was Wilkinson, for who the WMAP satellite is named for. They were getting ready to do their own observations of to try to detect the microwave background. Suddenly they get this call from these two astronomers at Bell Labs, and basically the Princeton group, to both their delight and horror at the same time, they've been scooped. They very quickly realized that Penzias and Wilson had discovered the cosmic microwave background. So they're excited, you know, that they wanted to see this and prove this Big Bang theory of cosmology, but they wanted to be the ones who discovered it. And suddenly it was found by two astronomers who weren't even looking for it, who are just trying to resolve this problem in satellite communications. And that's sometimes how science works. That, you know, and I mentioned this when I spoke to your group a couple months ago, some of the greatest discoveries in science and astronomy have come serendipitously, and this was one of those occasions. But you can also say that Penzias and Wilson, they did their homework. I mean, they eliminated every conceivable source of this background noise that they were hearing in their antenna. And when they didn't know what it was, they called the one group that could tell them what it was they were seeing. So even though their discovery was serendipitous, they still did their work very, very thoroughly and professionally. So there's some people who say, well, they shouldn't have gotten the Nobel Prize. I argue that, yes, they earned the Nobel Prize. Now, around the year 2002, when I was living in California, I heard Penzias give a lecture in the Silicon Valley lecture series. And he said that when he won the Nobel Prize, he said for a period of time, he was uncomfortable about it because he said, I never really viewed myself as a great scientist. But then he said that over time, he came to understand that Nobel Prizes are not necessarily given to great scientists, but to scientists who've made a great discovery. And that the discovery of the microwave background is one of the 10 greatest discoveries in the history of science. So yes, he made a great discovery with his colleague, Robert Wilson. I believe they earned the Nobel Prize.
Well, Wilson and Penzias were really engineers, and it proves something that I tell my son Justin, who's an engineer, all the time. Engineers do lots of great work, but they have no idea what they're doing till a physicist explains it to them.
Yeah. Well, and that's sort of what happened. And my understanding is that they did have training in astronomy, though, that they did have training in radio astronomy. So I'm not sure how much they were astronomers and how much they were engineers. But I agree with your larger point that, you know, they were given a job by Bell Labs. They did their job exceedingly well. And when they couldn't resolve the problem, they made the telephone call that could resolve the problem. But as I said, I would argue that Alpher and Herman, who I'm pretty sure they were both still alive at the time, they should have won the Nobel Prize for predicting this back in the 1940s. It was just that their paper was published and then it was largely forgotten. You know, not many people read it and it just fell by the wayside. And it's just kind of a tragedy of history that their work was forgotten. Having said that, their work is not forgotten now. You know, it's now any book you read about cosmology is going to mention their work and how groundbreaking it was for its time.
Cool. Any other questions for Bob?
Can you hear me?
Yeah.
There's Ken.
Yes,
Were you at
yes,
that
Ken.
Silicon Valley lecture? I was.
Yeah, actually, I was. I was out in the audience. Yeah,
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 we might have been sitting next to each other.
but I was, best as I knew, I was. I went there on my own, and but anyway, just out of curiosity, on the issue of the tension between the CMB measurement and the Type 1A supernova measurements, what's the furthest out that the type 1A supernovae measurements have gone to? And compare that to the distance out to the CMB, which I guess is about, what, 13 billion light years?
Yeah, we're basically seeing the CMB out to a redshift of greater than 1,000. We're basically seeing it back to the time when the universe was 380,000 years old. The farthest type 1A supernovae, I remember writing an article for Sky and Tel that it was about 8 billion light years away. But I am sure that since then they found even more distant type 1A supernovae. So I don't
Okay.
know what the current record holder is, but it goes pretty far. Certainly not, I mean, nothing we see goes as far back as the microwave background. But, you know, we can go really, really far back now with type 1A supernovae. And it's because, you know, they're stupendously luminous. You know, they're roughly the same luminosity as a type 2 supernovae, which comes from when massive stars explode. So we can go way, way back. And
Okay.
it's really important because the farther back you go, you know, you're probing different epochs in cosmic history. But also when you're looking at the local universe, the velocity of galaxies is somewhat contaminated by the motion of galaxies within their home clusters.
Mhm.
Those are called peculiar velocities. For example, the Andromeda galaxy is not redshifted, it's blue shifted,
Yeah, it's
meaning
headed towards us. Right.
it's moving toward us and we're going to collide with it in a few billion years. So when you go out into these very distant galaxies, you're really well out into the Hubble flow, and those peculiar velocities become totally irrelevant. So for a number of reasons, you know, astronomers want to go really, really far back and really, you know, really what they want to do is get very accurate and precise measurements of the entire expansion history of the universe, going back to the time when the universe was less than 1 billion years old. And I, you know, with that, that would be really key to understanding and unlocking the nature of dark matter or dark energy.
Well, the reason why I asked that question is that somewhere between 8 billion light years and 13 billion light years is when we're seeing this tension arise.
Yep.
So maybe the effect of the dark matter that you are suggesting is localized to that space between the 8 billion light years and the 13 billion light years.
And
And,
Ken, and that's a good comment, Ken. So I did discuss this in my astronomy magazine cover story,
right.
that one of the leading theoretical ideas for explaining this Hubble constant, and believe me, there's been a whole bunch of ideas put forth, and I explained some of them in the article, is that very early, this is after the inflationary epoch, but when the universe was still very young, like maybe a few tens of millions or hundreds of millions of years old, that the density and temperature conditions in the universe made dark energy work differently than it does today.
Mm-hmm.
And that because that dark energy in the very early universe operated differently than it does now, if you plug that into lambda CDM, that has the potential for resolving this Hubble tension. In fact,
Right.
you can even argue that that's the leading explanation right now, but there's other potential things. For example, there could have been in the early universe a different type of neutrino that no longer exists, and that neutrino would change conditions in the early universe in such a way that it would change the prediction of the microwave background or of the Hubble constant from Planck and bring it more in line with these other methods. So there's a whole bunch of different tweaks that you can make to theory that can resolve this discrepancy. We just don't know, and we'll have to get a better handle on the expansion history of the universe before we can really know which of these ideas you can throw out and which ideas show considerable promise for resolving this conundrum.
Yeah, I think there was an article about that conundrum, I think in one of the issues of last year's Sky and Telescope, actually. But I didn't have a chance to read the astronomy magazine article that you wrote.
I can
And-
send it to you. I'll send you the PDF, but you have to
Okay, that'd
promise
be
not to
nice.
send it
Good.
to any. I mean, it's
Okay.
been out for over a year now. I
Yeah.
do want to mention too, I have another astronomy magazine article coming up very shortly. And I don't want to give too many details because it's not published yet, but it's about the formation of supermassive black holes in the very early universe. And that's a
Okay.
really interesting problem because, you know, these different telescopes see quasars being powered
Yep.
by supermassive black holes
Right.
really, really early in the universe. And these black holes, you know, were containing like 1 billion times the mass of the sun. And kind of under traditional theory of how black holes form and accumulate mass, these black holes shouldn't be there. And yet they're definitely there.
Yeah.
So
Yep.
my idea goes into some theoretical ideas of how these black holes, these monster black holes, much more massive than the black hole at the center of the Milky Way,
Hmm.
were able to exist when the universe was still a toddler.
Well,
So that's
but
an
we should-
article you can all look forward to. And I
Yeah,
put a
I'm
lot of
looking
work
forward to
in
that.
that article. Yeah, I put a lot of work in that article, and it's fairly complicated, but I found it very, very interesting topic.
Oh, by the way, that the sky that you have in your background looks like the atmosphere as it was out here in California during the wildfires back in September.
Oh, wow. And
Well,
I
you
should
saw-
point out, this is a sunrise photo, not a sunset. And it was,
Benjamin Franklin is among us again.
yeah, that's right. Yeah, but it's a photo I took just out my front window a few months ago. And Patricia Ann Stratt, who was our originally scheduled speaker for tonight, she was going, you know, she was the one who said, oh, this is how you put up a background picture behind you. So I thank her for that.
Do we have any other questions for Bob? Anybody going once, twice? Bob, I think we're gonna spare your throat.
Okay, yeah.
Oh, Jan, are you saying you have a question or are you waving goodbye? Okay. Bob, thank you so much, both for filling in and for such an excellent talk. And I want to tell everybody that Bob's talk will be available as a video. I'll send something out to the listserv. If you got a notice for this meeting, you'll get a notice for the video. And it'll be available on YouTube and on our mine and Bill Waller's science magazine, the galacticinquirer.net.
And I want to thank Mike. After my last talk, he sent me this really beautiful sweatshirt with the GAC logo. And I told him earlier I couldn't wear it tonight because I'm in my basement where I don't get any road noise or anything. So it's really quiet down here. But if I wore it during my talk, I'd be sweating like crazy right now. But I have worn it. It's really beautiful. It's a great picture of Neptune, god of the sea. And I thank you very much, Mike, for sending that to me.
You're very welcome. You pretty much got the whole GAC haberdashery now, so.
Yeah, that's fine. Yeah.
You're for a fruit cake now, I think.
And I really miss, you know, going out for beers at the Halibut Point Brewery, or what was that other place we used to go?
The
On-
Cape Ann Brewing Company.
Cape Ann Brewing Company. That's it. Yeah, Cape Ann Brewing Company. I really miss going there.
Yeah, stay away from the pulled pork, everybody. It's not good.
Oh,
All
really?
right.
Okay.
Lights out. Thanks, everybody, for coming.
Thanks, everybody. Yeah, good
We'll
night.
have something good for you in January. I'm not sure what yet.
Halibut Point's unfortunately out of business. I used to
Oh,
bring
really?
powder from there every trip, and they're for sale right now. It's an empty shell.
Okay.
Oh,
Opportunity.
all right, thanks. Bob, if
Okay,
you want
good-
to stick
good to
around
see
for a
you,
minute, I'll
Bob.
show you how to put a video up as a background.
Thanks, everybody. Happy holidays.
Thanks. Bye.
Bye, bye, Elaine.
Michael.
Bye, everybody. Bob, at the bottom of your screen, you know where
There
the
you go.
start and stop video is, right?
Yep.
Well, if you click on the caret right next to that icon, you go to video settings. Bob? Bob has left us. Okay, everybody, lights out. See you, Eleanor. See you, Fritz. You can watch the first half. Anything you missed will be available as the video in a day or two. Okay, off we go. Bye-bye, everybody.